Okay. We are.
Hello, hello. Do you hear me now? Do you hear me?
Yes, perfect, Cedric.
Okay, great.
So thank you for watching us live on YouTube and here in Google Meet. Welcome to the Nanos Colloquium organized by the Nanoscience and Advanced Materials Graduate Program of the Federal University of ABC, UFABC. Today we are pleased to present Professor Martin SVEC of Czech Academy of Science. I also would like to thank Professor Cedric for helping us bring Dr. SVEC to this seminar. Please, Cedric, could you introduce Dr. SVEC?
Okay. Thank you, Pedro. It's Schwarz. Martin Schwarz. SVEC means shoemaker, right, Martin?
Yes, exactly.
Okay, so they say that in Brazil, we say that a good shoemaker makes a pair of shoes a year. And we are very eager to see the more than one pair of shoes that you have been making in the past few years, Martin. It is a pleasure having Martin here. So I met Martin back in 2006 in Manaus at the beautiful Hotel Tropical. It was a gorgeous place, and now it is being eaten by the jungle, abandoned for about 4 years, unfortunately. But anyway, when I met Martin, I was in my PhD, and so was Martin. Martin was working with Professor Vladimir Hab in Prague. And after that, Martin spent some time in Spain for a postdoc. And then I met Martin again in 2014, if I'm not mistaken. That was in Prague. And Martin was there working with Pavel Jelinek, who has also presented a seminar for us a few weeks ago. And at that time, Martin and Pavel, they were working on, it struck me very interestingly that they had built their own CVD machine, and they were studying graphene. And they published some very interesting papers on that. And about at the same time, they were studying molecules on surfaces, including graphene. And many of the devices that their group used were homemade, which was very interesting to see. I saw Martin again, I think it was 3 years ago in 2018 in Prague. And then Martin was already moving more towards the molecules examinations and optical properties of molecules. And soon after that, Martin started his own group at the Physical Institute in Prague. So Martin is not really a professor because his time is mostly devoted to research. Martin recently hired a Brazilian postdoc. Gustavo is his name, Martin? I forgot.
No, it's Rodrigo Pereira.
Rodrigo Ferreira from Unicamp. So Rodrigo was able to go to Prague before the pandemic crisis really hit hard. Unfortunately, the Czech Republic was doing very well in the COVID outbreak at the beginning, but then they lost it. I'm sorry to say that the Czech Republic also went through 4 health ministers in this period, right, Martin?
Yeah. We had a lot of ministers and a lot of dead people as well. So I understand what was happening in Brazil as well.
Yes, and this Rodrigo postdoc who is working with Martin, he just had gotten a position at Tech, which is, as some of you might know, which is the estatal company in Rio Grande do Sul. It was the only company in Latin America that was able to produce chips, semiconductor chips, and it has been dismantled by our government, and the parts are going to be sold as junk, unfortunately. But I'm happy to know that Rodrigo was able to Martin and go to Prague and follow with his career there. So Martin today is going to talk to us about his research on molecules, optical properties of molecules. So Martin, thank you very much for your time, and it's a pleasure having you here.
So thank you, Cedric, for your very nice introduction. I actually didn't know. So what I will present is our research, which we did in the past, let's say, 3 years. In this group, which Cedric mentioned, of course, with the courtesy of Pavel Jelinek, who gave me the nice opportunity to make my own group and to run my own experiments with the ideas that we would like to pursue also in the future. So I would like to introduce a little bit the field, because you already have heard from Pavel Jelinek about the types of that we do and the types of research that is common for our group. And we are mostly dealing with atoms and molecules because we are able to see them in our instruments. And actually, for us, the main reason is are not applications or some revenue, but it's because we find it really fascinating, and that we can see really inside the atomic and molecular world. So I can hear someone's having the microphone on, so maybe you.
Yes, Cedric.
Yeah. But do you hear me well? Sorry.
Sorry about that. Yes.
Good.
We hear you, Martin. Yes.
Good. Just, yeah, feel free to interrupt me if you don't hear me or if you have any questions in the course of the lecture, please. So, so seeing the atoms and molecules in their own world is a unique opportunity to understand the fundamental physics which happens at this scale. And this includes really purely quantum phenomena in the realms of magnetism, electronics, and photophysics, which is our interest now. Of course, if we get so advanced to understand enough to construct some useful devices, of course, one can envisage some kinds of machines, nanorobots, and nanoelectronic devices that could improve our lives. Actually, I have to mention that this idea is not new, and it has been already mentioned by Richard Feynman in his famous lecture, which was having the title "There's Plenty of Room at the Bottom," which he gave in Caltech in 1951. So he was a real visionary, and he already had in mind the kinds of possibilities that we would get if we can access the nanoscale. But as I said, so I'm mostly interested in photophysics, and that actually is closely related to the things which probably most of you have at your homes or even in your pockets, and these are the organic emitting devices, like the organic emitting LEDs, LEDs, the diodes. And these are based on organic molecules that have the property that they can be excited and they would radiatively de-excite. And that can be achieved by various means, but the most common used in electronics is by electrical means. So by applying some electrical current, these molecules can be excited and emit light. But these devices are usually composed of many layers of these molecules. So what I'm interested mostly are single molecules, because it is a well-known fact that these molecules typically absorb and emit quantums of energy in a single unit. I say mostly because there are also some more exotic processes like two-photon absorption or emission, which can be also used in the quantum cryptography world because they can carry this entanglement information and so on. The main question in these kinds of objects is how we can get a signal reliably for something so small. So this is a great question, which boils down to the technology which is available at these days. And looking at common optics, which is a well-established thing since the long ago, it is clear that the optics itself doesn't have the resolving power to resolve individual molecules. Of course, in the modern optics, it is possible to approach single molecules if the studied objects are enough diluted. That means that the concentration of molecules is really low. But what am I talking about is a real resolution at nanoscale, so really nanometers or similar. So in the traditional optical world, it is well known that it's not possible to achieve anything better than like half of the wavelength resolution of the light which is used for resolving the object. So if I have a point source that has a certain wavelength, the so-called Abbe criterion says that I can only resolve it as a projection which would carry this kind of size, which is defined by the wavelength and the numerical aperture of my system, of my optical system. This guy who invented this criterion, he spent part of his life in Germany, in Vienna, trying to improve the optical microscope. And he soon realized that this is the major limitation in the resolution of optical microscopy. So there is a solution in the modern technology, and that's plasmonics. This is a relatively new subject of physics, of photophysics, which is concerned with so-called plasmons. So these are collective excitations of electronic gas, usually near to the surface or also in the bulk of metals, which can be characterized as a quasi-particle. So typically, if a light is shined onto a metal which has this plasmonic property, the plasma would be excited on its surface or in its bulk, and then it can be re-radiated back into the free space. And the subject of science, which is concerned with properties of various shapes of metal particles and waveguides, it's called plasmonics. Plasmonics has actually applications already. So, for example, very interesting is that it's possible to use plasmonic nanoparticles to stain glass with certain colors, because the size of nanoparticles and the metal would define the color at which the thing absorbs or emits. And it is also known that when there is some kind of apex on a metal, or when there are two apexes near to each other, that the optical density of state is increased many times, like orders of magnitude, and this can serve to actually collect signal from excited molecules. And this is exactly what we are going to use, this principle, which is called nanocavity plasmonics. So we create a nanocavity by having a microscope, which is called scanning Pro Microscope, and it's consisting of a conductive tip, which is made usually of some coinage metal. So in our case, it's platinum iridium, but coated with silver. And we have a substrate which is metallic, but also covered by a salt island to decouple slightly the molecules which we put on the top. And the space between the electrode, between the tip and the surface, is called nanocavity. And this is what allows us to see photons originating from a single molecule. So this is just a schematic setup how it works. And in fact, it's a relatively complex instrument, which is terminated by there is a lens which is refocusing the light outside from the instrument, from the vacuum to an optical fiber, which can be then connected to a spectrograph that gives us the actual spectrum of a molecule. So this is very nice tool, because this really allows us to point at the molecule and get the optical signal from that. So this is how our laboratory looks like. You can see the machine on the left. The cylinder there is the Cryostat, which actually consists of two liquid vessels. One of them is for nitrogen, the outer one, and the inner one is for helium. So like this, we ensure that our samples, our microscope is always at the same very low temperature. So we are working between 4 and 10 kelvins. At these temperatures, systems are very stable and very well defined. So I know that on my sample, I have only the clean metal and only the molecules. And I can really prove that by making images of these things. So this is the scanning head of the microscope. So it's quite a complex thing. But what you can see here on the right is the scanner with a sensor attached to it. So this sensor actually combines atomic force microscopy, scanning tunneling microscopy, and this optical spectroscopy, which I was mentioning, into one sensor. So in a zoom, it looks like this. So this thing is the sensor holder, and this at the end, this thing which looks like a piece of electronics is very tiny, and it's a cantilever of the atomic force microscope with a very tiny tip attached to the end. So this tuning fork, as we call it, is oscillating, and by tuning it into resonance frequency, you can measure the force which is acting on the tip. This is a lens which is attached from the other side and allows me to see, to really focus on the end of the tip, on the nanocavity. And our tips are cut by focused ion beam. So this is a special device which focuses high energy ions and is able to cut the tiny wire. So this wire has 50 microns in diameter, and the focused ion beam can cut it in a few seconds, as I hope will show you in this video. This is the wire. Here you see the cut propagating, and at some point the wire is cut. So the other end holds there only by static electricity. So if you shake the tip, it's going to fall off. So this kind of tips, I would like to, yes, this kind of tips when zoomed are, they look quite rough. But believe me that it has a lot of very sharp points at the end. So we always have some atomically sharp end to work with. So what we need is just a couple of atoms at the end of the tip, so we can resolve individual molecules. Right. So what we do is we approach such a tip to the surface. We focus our optics, and we start to send tunneling current through it. What it means is that electrons, when we have this electrodes polarized by some voltage, they tunnel spontaneously. If the gap between the tip and sample is at the order of nanometers, so-called tunneling current will start to flow. And the decay of the energy, of the excess energy which the electrons have with respect to the sample, has to be dissipated somehow. So most part is thermalized, so it's changed into, the energy is changed into temperature or some, movements, vibrations in the crystal, and that gets eaten by the cryostat. But some part actually is converted into plasmons, and surface plasmon polaritons to be precise. And these things can radiatively decay, and we can actually detect them. So we can get a spectrum of the nanocavity response, so to say. That depends on the material which is used and also on the shape of the tip. So there are some works which even shape the tip very precisely to get a very specific spectrum of the nanocavity. But we are okay with almost anything. So we just need the optical response in the region which is interesting us, where we expect that the molecules will emit. So our plasmons look like this in the logarithmic scale. This is the intensity versus plasmon energy, so which is basically the wavelength just converted to electron volt. And depending on the voltage which we apply, the plasmon has a different cutoff. So by increasing the voltage, we can control the cutoff energy of the plasma, the highest energy photons that we get from the nanocavity. And this is actually quite great because we can calibrate our optics with that, and we can also calibrate, for example, radio frequency modulation, because this wiring which you use in the microscope has a very complex transmission function. And to characterize it in situ, that means like when everything is connected and the system is cooled down to the working temperature and the sample is prepared, we can use the plasmon edge to calibrate the radio frequency amplitudes. So some people use radio frequency to, for example, investigate spins in the system by tuning them into resonance with the radio frequency. And this, before this, they need to calibrate the amplitude to drive the nanocavity always at the same amplitude. So this is one of the ways, and we have actually tried it. And by increasing the modulation voltage, you can see that the plasmon edge is also moving up in the energy. And there is a nice proportionality which can be used for the actual calibration of the wiring. So as you see, it's very complex, but we can achieve calibration in a very broad range of frequencies, up to almost 20 gigahertz. So this kind of usefulness it has. But I would like to focus on the molecules. So am I still heard very well?
Yes.
Good, thank you. So excitons and single molecules, what it is? Exciton is actually also a quasi-particle which represents an excitation of a molecule. Molecule can be excited either as it can have a charge or it can be neutral. So in the basic case, exciton would be a neutral, although it can be also viewed as an electron-hole pair located on the same molecule. This is called so-called Frankel exciton. This is associated with some optical gap energy, which corresponds to the energy of the photon that could be emitted from the system. So in a very simple way, one can imagine that as moving one electron from the highest occupied level to the lowest unoccupied. So I will get this kind of situation, which when it recombines, emits one photon. This is traditionally schematically represented by so-called Jablonski diagram, which works with different excited states of the system. So here the S0 would be the ground state. So when the molecule is neutral and has no excitation, S1 is the first excited state, S2 is the second, and so on. And these horizontal black lines, which are not thick, these would be vibrational levels of the system. So on top of an excitation, the molecule can also vibrate, increasing its energy slightly. And from these states, in between these states, there can be some transition. So the basic one from the first excited state to the ground state is called fluorescence in chemistry. In physics, we call everything luminescence. But I think actually chemists distinguish between fluorescence and phosphorescence because when the system decides to go to the so-called triplet state, which is a configuration of spins on different levels like this, then the system takes much longer to decay, just because of the basic exclusion principle. We cannot decay the system without turning the spin again. And that would be phosphorescence, and usually is associated with very long lifetime of the excited state. So this is something which we cannot detect because you wouldn't get enough signal from a single molecule. So instead, like the vast majority of the studies that we do is on fluorescence on single molecules. And there is one important point, which is a difference between absorption and emission. So the quantum of energy which is absorbed doesn't correspond exactly to the quantum of energy which is emitted from the system, because there is some geometrical and electronic relaxation between that represented by the Stokes energy shift. So it's also known in Raman spectroscopy and so on. So like 2 years ago, we tried our first experiment with a camera that we borrowed from another group because we didn't have our own, and we tried the system which is zinc tungstenine on 3 molars of salt, and we were able to actually see a single molecule emission. So this is an image of the surface as it looks like. This is the salt, and these are individual zinc cyanide molecules. There are various kinds. Some of them can be stabilized by being attached to an edge on the surface, and others are, we call them rotating or dynamic, because they oscillate between two orientations. This is induced by tunneling current. This movement can be also proven by the current. When we place the tip over one of the lobes of the molecule, we can see this kind of telegraphic noise that corresponds to the rotation of the molecule. It's a random process. Both of the configurations have the same emission energy in photons. We can actually correlate the photon signal with the other channels that we can measure. So if I begin from right to left, so on the right part, there is something we call photon images, and they are constructed as following. So we place the tip over every pixel of the image, and in every pixel we measure a spectrum. From that spectrum, the energy of emission of the molecule, then we draw one slice, one image, and this is what we get. Then the atomic force microscopy image is actually showing the molecular backbone because it's sensitive to the very atoms. So the forces in between the tip and the molecule are driven by Pauli exclusion principle, and that allows us to see the benzene rings and the other structural motifs within the molecules. This is very good for geometrical registration, and you can really see that on the molecule which we consider as rotating, the molecule is switching between two orientations. We can even identify the angle quite precisely. Then the STM channel shows us the tunneling current, which in this case corresponds to the highest occupied or lowest unoccupied orbitals. And then the traditional STM topography in a constant current shows us something similar but more blurry. So this is what we can measure with this technique. You can correlate a lot of signals together. Now let me show you a thing which we did with copper cyanide, which are very similar, but they have one important difference, and that is that they are more happy in a stable configuration, even though they are not attached to any defect. So we can actually force them to convert from the initial rotating state to the stable state. And this change in the spectrum is associated with a shift in the energy of the photon emission. It is about 20 millielectron volts, which in the optical world can mean is quite a lot actually. So it doesn't seem like much, but it's quite an important shift. And this is something that we first thought might be associated with a property which is called in traditional chemistry solatochromism. That means change of the color of molecule according to its chemical environment. So we investigated a little bit more with the atomic force microscopy and with STM getting closer with the tip to the sample to see also the lattice of the salt which is under the molecules to register precisely the absorption position of these molecules. And we actually realized that the stable molecule sits on a sodium ion, whereas the rotating one is sitting on chlorine. So that already obviously gives it a slightly different chemical environment, because on the surface of salt there is a strongly varying electrostatic potential. So these are calculations made by BFT, which shows a geometrical model that nicely agrees after relaxation with what we observe in the experiment as well. These are pictures which represent the electron density of the two configurations, and one can actually make simple numbers out of that. seeing that the two configurations reside on different numbers of sodium and chlorine ions, which is actually a very nice explanation why it should change its emission energy, because the whole configuration will be influenced by the different acting of the electrostatic potential of the surface. So this is really analogical thing to the solatochromism. There is another interesting.
Excuse me, Martin.
Tell me.
Could you go back to the previous slide, please?
This one?
Yes, I'm not sure I fully understand it. So on the left, and you have in red and in blue where the charge density increased and decreased.
Yes.
Relative to what was that increase and decrease?
Relative to the freestanding molecule.
Okay, I see. And at the left and at the right, you have a different rotation angle relative to the surface.
Yes. So the left one represents the stable configuration, and on the right represents the rotating configuration, which is composed of two symmetrical rotations.
Okay, and you were saying that these images, they explain why the molecule should rotate. Could you please explain that again?
So the reason for rotation is just the total energy of the system. So if you place the molecule over sodium or chlorine, it would try to minimize its energy, of course. And in one case, it is adopting this kind of orientation, and in the other case, it's actually oscillating between two symmetrical positions, which are rotated like 11 degrees with respect to the main axis.
Okay, I see. But
so the theoretical calculation by evaluating the total energy of the systems is able to reproduce this behavior. And what I am showing here,
yeah, I see. I was just
uh-huh.
I was trying to understand how the different charge distribution would point to a rotating force in the system. This is not clear to me.
So I was not claiming that the electrostatic field is somehow influencing the rotation or stability of the system, because I see the electrostatic potential as a factor in the emission energy. Okay, in the optical signal I'm getting. So the energy of photons which I get is clearly influenced by the electrostatic acting of the surface on the molecule. Yeah.
But if I'm not mistaken, here on the right, we can see that there has been a variation on the surface that we do not see on the left. Is that correct?
Yes. I mean,
yeah, there is a little lobe there.
Yes, you are a theoretician, so you know it also depends on where exactly you draw the ideal surfaces. So there is also some acting on the left, and you can actually partly see that here there are some blue increase of electron density on the surface as well. So it's located. It's located, if I'm not wrong, to the chlorine atoms.
Okay. Thank you, Martin.
Yes. So let's move on to a even more interesting effect that we can achieve by applying bias voltage. So if the bias voltage, some people, actually Guillaume Schul, he's a professor with his own group in France, and he's working with similar instruments, and he actually published a science paper in which he very nicely demonstrates that the bias voltage polarity, when applied on a zinc tungstenine deposit on salt on gold, he can change very drastically the emission energy from 1.89 electron volts, which is like red color, to 1.52, which is, no, if I'm not wrong, that's almost infrared, or that's already not visible, I think. So this is a very large effect But it's interesting that in the second case, when the bias voltage is below 0, he actually sees both kinds of emission. So it's not purely the 1.52 electron volts, but he also has a little bit of contribution from the energy which is dominant at positive voltages. And he calls this phenomenon electrofluorochromism. So in other words, emission color influenced by electrical field. So we decided to do a similar experiment, but we changed the substrate to silver. So the difference between gold and silver is the work function. So we get a different alignment of the HOMO and LUMO levels with the surface level. And that's very important, because then we can achieve conditions in which we get almost the identical intensity of the emission from the state which is excited by the voltage in the case of gold. So I should be more precise in saying that this thing was interpreted as the molecule being in neutral and cationic state. So what Guillaume Jules is claiming that actually you can bring the molecule to a cationic state by the field and excite it as well. So let's call it cationic emission and neutral emission, or also in other nomenclature, it can be a trion or an exciton. Trion because it comprises of 3 trapped charges, and exciton only of 2. So we can achieve conditions in which you have a trion and exciton at the same time from the system. Now, this is dependent on the position of the excitation. So it depends on where we place the tip inside the molecule. We can promote one or another. And it seems that it's a relatively complex behavior, which I will show in the next slides, can be mapped by making the photon maps. And we see this is a very interesting effect also from the point of view of energies, because if I increase the voltage, so I get an emission from the excitonic state, so from the neutral exciton, and only over some threshold, I will start to see the lower energy emission. So this is a little bit paradox. So I have an emission which is at higher energy, and then I increase the driving voltage, and I get an emission at lower energy. So this is very curious. And I can map it in the space. So here is a table, the photon maps. And I'm beginning at minus 2.3 volts, increasing the absolute value of bias to 3.2. And you can see that exciton is somehow evolving, but a trion is first not present, and then above the threshold, it appears very sharply as this nice coral. So this is a nice example of how the photon maps can be used to see all things at the same time, including the threshold and also the spatial variation of the emission of the molecule. So what do we see in the photon map? So to answer that, I would like to show a little bit what it could be, like how we model it and how we understand it. So in the quantum chemistry world, this is quite common, and it is very well known that an excitation of the molecule can be represented by a so-called transition density, which in fact is nothing else than a multiplication between the orbitals between which the electron is having the transition. So this is a very simplified picture. In fact, it's a many-body process, so more orbitals get involved in it. So typically this is composed of more levels. So I'm just showing the zinc Toscana because it's a nice example, and in a neutral case, it really corresponds to the HOMO transition. And the transition density would look like this. This, in principle, can be represented by a transition dipole if we make the expansion, the Taylor expansion into, or the multipole expansion. So we get dominant contribution in the dipolar moment. So there will be a negligible amount of quadrupole and higher multipoles. So this can be used for simulation of the photon maps. Of course, we have to look also at the trion, how the charged exciton will look like. And surprisingly, these two transition densities are almost identical. So when the exciton is modeled, so we just put it into some code which we did, and so we can get a photon map by summing two photon maps for the independent dipoles which are perpendicular to each other on one molecule. We get something which closely resembles the photon emission we measured. But for the trion, it's a mystery because it's a completely different picture, and we are actually expecting something like the exciton. So for that, we have to look into the process, what's actually happening inside the molecule when it gets excited. So this can be imagined as a stochastic process in which we begin with a ground state molecule, and we are injecting some charge by the tip. So in this case, these are holes. So the holes, if they get captured on the molecule, it will be created a transient cationic state which has to capture an electron from the surface, and at that point it will form an electron-hole pair, which can eventually decay. So all these processes can be modeled by stochastic models, and each one is associated with their own rates. So this is possible to recreate by considering some rate equations. But if we have a more complex system in which this can actually convert. Sorry, in which it can convert a trion. So there is a point in the diagram where the system can split its behavior into simply decaying or convert into a trion by capturing another hole. And these two processes are competing. So this is actually anti-correlated, as I will show. And this actually, this rate is associated with the probability of moving the system from a simple exciton to a trion. And that's represented by our photon map here. So in fact, this photon map is just a probability of bringing the system from the exciton to a charged state. So as I said, so we try to model these things as a stochastic process, and also try to make a measurement to measure the lifetimes of the excitons in the system. So with my colleagues, we devised a scheme in which we modulate the voltage on the tip by a 200 megahertz radio frequency and see how the optical response is delayed from the base signal. So first, we calibrate our system with the surface plasmons of silver, such that we get a reference phase of the signal. And then we make the same measurement, but on zinc tungsten. This provides us some kind of phase difference, which can be converted quite easily to the lifetime in the system. As an example measurement, so here we measure the plasmon. You can see it's very nice, smooth curve, which can be fitted very nicely. And then measuring the lifetimes on the energies of the exciton and the trion separately. So for each one, we use an optical filter to filter out just the energies which are corresponding to each excitation. And we can measure different kind of delays. So these phase shifts, as I said, can be converted to the lifetime directly. So in the exciton, we get something around 600 picoseconds, and for the trion, we get 350 picoseconds. Actually, this is more complex because by changing the bias voltage or the opening of the gap, the lifetime would change. And that's expected because, for example, by opening the nanocavity, we are increasing the coupling of the system to the tip. So we are letting the excitons live longer on the molecule. And with the bias, of course, when we reach the threshold, then the lifetimes would drop both at the same time. Then we tried the same experiment just for comparison on gold, and we realized when we open sufficiently the gap, we can reach the lifetimes which are compatible with measurements in solutions. So this point is corresponding to 5 nanoseconds, which has been also reported by chemists who measure the fluorescence in solutions. So we also try to run the system in what we call overdrive, means modulating it over the threshold, but really a lot, such that we are exciting the trion only in the upper half of the sine wave. So the exciton is supposed to be excited in the whole region of the sinusoid, but the trion only in the upper half. So this is what really happens. That can be seen here, that this is only the upper part of this sinusoid. It also makes a big dent in the exciton. So this is an evidence that these two processes are anticorrelated. In other words, they can happen only one of them can happen at the molecule at the same time. So the molecule has to decide, like I said, if it goes to the exciton state or if it goes to the trion state. We tried to simulate it by the rate model, and we got a nice agreement, including the intensities, the relative count. So this is just to show how the zinc toluene can be, how a single molecule can be really interesting from the point of view of photophysics, and that there are still many open questions about like how exactly the excitons behave in the system, like how we can influence them by the field and by the selection of the substrate. Things can get even more interesting when we interface the molecules together. So it has been shown in the very past that when we have some clusters of molecules which can have an exciton on them, that the exciton can under certain circumstances delocalize. So this is a typical, very exemplary quantum effect. That has all the hallmarks of the quantum entanglement, which means that the exciton is at the same time at both molecules. This has been discovered by chemists, curiously, not by physicists in the past, by this guy whose name is Frankel. And it has been shown very recently with a very nice visual observation by a Chinese group that this can be also done in our type of microscopes. So by putting two zinc toluene molecules together, this could observe the typical splitting of the single excitation emission to various peaks. So they made maps at each individual energies, which they can see in the spectrum, and got a series of maps, which they were able to explain by simulating photon maps with the corresponding dipole orientations. So these arrows in the pictures represent the transient dipole mutual phases. So when they are in phase, the system has the strongest emission, and it would look like this. So the maxima in the photon belt would be concentrated on the outer part of the island, of the cluster. Whereas if they are out of phase, it would be in the center. There's the mode 5 here. But in this case, it's relatively complex because we have more dipoles interacting. So it's kind of difficult to create all the possibilities and to simulate it and to compare the experiment to the theory. We have instead selected a more simple system, which is a Berlin tetra, how it's called, PTCDA. It's the most studied molecule ever. I will show you the geometry soon. So we deposit this molecule on the salt layers and anneal very slightly, like to 100 Kelvin. They actually diffuse and form small islands. So we have chosen the smallest islands of all, which are typically dimers, trimers, and mostly tetramers, because we try to understand what is happening in these systems. So first we begin with a monomer. This is the molecule, the tetracarboxylic acid, yeah. And this is the current map, and the geometric will superimposed. So you can see that we actually see something which corresponds to the lowest unoccupied molecular orbital. This is the AFM picture, which is nicely showing the pyridine backbone. And this is the spectrum that we get when we apply minus 2.5 volts. We attribute this emission to an anionic state of the molecule because it's well known that this molecule, when it's deposited on metal and decoupled by the salt layer, we would get one extra electron on the molecule. So actually, it really has a half spin, and it has been proven in other works. And this is the nice emission peak that we get out of it. So this is the main emission energy with the side bands, which represent the vibrational levels. So the vibrational losses and gains of the transition. Here is the calculation or schematic representation of the result of calculation that we get when we calculate the first excited state of this anionic molecule. And that's composed of over 30% of transition between LUMO and the LUMO plus 1, and then 66% between HOMO and LUMO plus 1, I guess. Yes. So this together with the transition density, which is drawn here, represented with a big arrow. The big arrow here is again the transition dipole. And the photon map, which we measure and which we simulate, they are very similar. Of course, they have differences, but these are caused mostly by the tunneling current modulation. So we don't have any current on the axis of the molecule. That's why these lobes are interrupted in the middle. When we put together like two molecules like this together in this arrangement, so we found them on surface like this, and it was quite a frequent motif. We get a spectrum which is composed of two peaks. So depending on where I measure in the cluster, I get different spectrum. So if I measure in the middle, I get a maximum at lower energy, at higher energy. And when I measure on the outer part of the molecules, I get a maximum which is stronger and at lower energy. This can be mapped again, and I get this distribution of intensity for one peak and for another one, which can be compared to simulations of photon maps, considering the in-phase configuration of the dipolar moments of transition densities and the out-of-phase ones. This comparison is gives quite a good agreement. Then another motif would be perpendicular, and in that case, it's quite different because, of course, I get the main dipolar moment from one of the molecules is the lowest energy, but then it gets more complicated. And actually, we get involved something which looks like a transversal dipole. So this molecule apparently doesn't only have an excitation on the longer axis with the dipolar moment on the longer axis, but also on the shorter axis. So this is very interesting because it becomes dominant in the third excited mode, and it's really like the agreement again between the theory and experiment is quite good here. So we have a very good evidence that this so-called transversal dipolar moment plays a big role in the system, which is not the case in the neutral molecule. So I would like to say that coupling between anionic molecules could have very different properties from what we know on neutral molecule, which is actually the subject of the most of the studies. So I haven't found, maybe someone will correct me, but I haven't found almost any examples of anionic molecules coupling in themselves. So this is another structure, which is a trimer. as evident by the nice parallel backbones arranged in this way in the AFM picture. And here, surprisingly, we only find 2 levels. So I would expect in such a system more splitting in the emission, but I only get 2 energies. Why is that? Because this system apparently somehow tries to equilibrate the excess of charges. So apparently 3 charges for such a small cluster are too much. So it tries to compensate by putting the middle molecule on neutral level. This is also seen by the current image, because in the middle we are missing the characteristic feature of the lowest unoccupied orbital. So base level is not accessible for tunneling, therefore we don't see it. And we assume that, or we deduce that there is a neutral charge molecule. And indeed, these 2 levels really correspond to the in-phase and out-of-phase configurations of the transition dipoles, as evidenced by the agreement in the theory and experiment. This behavior can be usually influenced by applying a different bias. So we can apply a large positive bias, and the system spontaneously will switch into a 3-electron configuration. And also the excitonic properties will change very drastically. So in this case, I get a new mode at the lowest energy, which corresponds to the dipolar moment of the middle molecule, very weakly coupled to the out-of-phase mode of the peripheral molecule. And the mode which previously has been at the lowest energy here now is the second lowest. So it's actually preceded by this one. So this is a nice way how to switch the excitonic properties only by applying different voltage. So maybe I would like to just show a last object, which was a tetramer. And there things really become more complex. We see more peaks, and we cannot fully explain what's happening in the system, but it still roughly matches with the dipolar approximation. So we can still approximate the system by placing dipolar moments and simulating photon mass. So at the end, I would like just to say who was the main protagonist in this experiment. So Ilka Dolezal was the PhD student who did most of the measurement. Sophia, she calculated all the nice transition densities, excited states, and photon mass. And Rodrigo was helping the experiment a lot because he's here only shortly. So I'm expecting him actually to do more nice experiment in the future. And Pablo was my friend and consultant in writing of the papers and giving us always his feedback on the experiment, because he's an expert on the field. So I would like to thank you very much for your attention, and I hope I will get some questions.
Thank you very much, Martin, for this really didactic. For theoreticians, it's really nice when you see the theory in real images. So now it's time for questions. If you have any of them, please raise your hand using the emotions here below in Google Meet. We have Paula. Paula, please. Paula?
Okay. Yeah, just turning on. Thank you for your amazing talk. I love it to see these pictures on dyes I have studied for so long. I've been working theoretically on calcianides and porphyrins and so on. So it's amazing to see them. So let's see. I have a lot of questions, but I'm not doing them now. Maybe we could change some mails. And
yes, sure.
Yeah. It's amazing you are able to measure these fluorescent experiments with so short lifetime scale. It's amazing. You can see that. It's very hard to see. So very nice, very interesting. And we have problem about porphyrins. We have studied porphyrins are a bit different from phthalocyanines because the orbitals that are involved in transition are not the LUMOs. We have 2 LUMOs and 1 HOMO for phthalocyanines. For porphyrins, you have 2 HOMOs and 1 LUMO. The symmetry is a bit different. So I'd like to know if we have 2 degenerated states and at the ground state, how they could change your experiments. And something that could be very interesting to see, we have published a paper about cobalt phthalocyanine that's with our computational strategies. It's impossible to see what the ground state, the state of the ground state, if it's triplet or if it's singlet. It's impossible to see computational quantum chemistry. No? And if you could see that with these experiments.
So I actually don't know if you are asking about porphyrins because we didn't have any experiments on porphyrin. So
just to see, they are very similar to phthalocyanines. If you could see, if
so on zinc phthalocyanine, this measurement was working very well because the lifetimes are relatively long for our instrumentation. So of course, when we are talking about 50 picoseconds, that's already too low. But if it's around nanoseconds, that's perfect for us, especially on this gold substrate. We got values as I have been showing here. And the ground state question, so actually here, as you see, the system is somehow oscillating between actually the ground state itself is neutral, but it's always undergoing a lot of changes. And at some point it's single cation, and then it converts either to exciton or then furthermore to the trion. Which we find really peculiar, but it could be also just the function of the setup. So maybe when you dissolve these molecules in a solution, things can work differently, you know.
Yeah, I see.
I don't know if I answer your question, but you may write me the question so I can understand better what is your interest.
Okay, thank you.
The next one will be Cedric.
Martin, congratulations for the brilliant work. Really, really nice and
Thank you.
Very nice presentation, extremely clear. It was a pleasure to see it again. And I have to apologize beforehand because in 10 minutes I'll have to leave to get my daughter from school. But before that, I'd like to ask you 2 simple questions. And then, of course, we can keep on chatting through WhatsApp. So the first question is, I haven't seen you mentioning anything about temperature in your experiments, but I think it's an important parameter. And is any of that visible at room temperature, or do you have to really go down to very low temperatures? The second question I have for you is, when you talk about entangled excitons, that puzzled me a bit because the vision that I have about entangled photons is that, for example, if you mess with one photon, the other one will correspond to what you did even at large distances or entangled electrons. But what exactly are entangled excitons? I mean, isn't it simply 2 excited molecules interacting with each other? So how is that notation different? So these are my questions.
Yeah. So the first question is very simple. So I can tell you that we are working at 8 Kelvin, and we haven't tried at higher temperature, but I expect it could work as well. You know, there is no reason why it shouldn't. Of course, things can change because of the temperature, of course, but at this point, I cannot tell more. And the second question, so what I mean by entangled excitons, actually I'm talking all the time here about single exciton excitations. Even on the cluster which are made of 3, it's still one excitation only. So it's not 2 molecules both excited interacting between them. No, it's just a single exciton which actually doesn't know on which molecule it should be first. So it's a real kind of quantum delocalization effect, and it can be represented even by Hamiltonian. So you would construct it by putting on the diagonal, you put the eigenenergies of or the on-site energies of the individual molecular units, and then on the off-diagonal you will put the couplings between these molecules. And these couplings can be evaluated as the dipolar interactions, the Coulombic, some Coulombic integrals, which you evaluate from the two transition densities of the molecule. So by solving this Hamiltonian, you will get eigensolutions, eigenvectors of the system, which will correspond each one to a different energy, which we are actually measuring here, in the experiment. And to each eigenenergy, you can assign like one general transition density for a system that can serve for simulation of photon map. So I'm talking about single exciton excitation delocalized over the molecules. This is what I mean by entangled exciton.
Okay. Thank you very much, Martin. Thank you once again. And I'll say goodbye for now and see you later.
Thank you very much, Cedric.
Very good.
James, we have I guess we have 2 questions from YouTube. Can you make just one? And after that, we include Mauricio in this conversation.
Yes. So we have a question from Shadi Fataya. He said, "Hey Martin, nice talk. I have 2 questions. First, a silly one. How many electrons need to tunnel until 1 photon is emitted from the STM junction?"
So hello, Charlie. I didn't know you were listening. If I knew, I would say something different. Okay. So to answer your question, how many electrons I need to tunnel before 1 photon is emitted? So you are asking me actually about quantum efficiency, if I'm not wrong. And I would say I don't know this number precisely, but it's very, very low. So I need to. So imagine. For example, I'm tunneling at 100 picoamps, and I'm getting from the system like 1,000 photons. And of course, my optics is only catching like 3% of the photons which are emitted from the molecule. So from this, you can maybe figure out what's the exact number of the quantum efficiency. So I would say it's pretty low. So because 100 picoamps contains a lot of electrons.
Mauricio, please.
It was a very nice talk. So congratulations. So my question, if I understood correctly, that the photons are emitted when you have a bias, right? When you have exactly the tunneling and the potential difference by the tip. And how do you do the calculations to compare your measurements to theoretical data? Because as I understood, you would need to do the calculations under a bias, right? Unless I misunderstood something.
So you are asking about the process of simulating the photon maps from...
Exactly, yeah. In your states also, your state's energy, if you need to put the bias between your tip and your support, right, your substrate.
Mm-hmm. So actually, we don't put the bias, and I believe we don't have to, because we know which kind of transition it is. And the bias here is only serving to excite a particular excitation. So it's not, it doesn't need to be included in principle in the calculation. And the photon map is calculated as following. So first, I get from our theoreticians the transition density, which I said is some kind of product, some kind of multiplication between the orbital between which the transition occurs. So this transition density, I can plug it inside a code which is based on a convolution. So I represent the nanocavity field by some kind of multipole. So in our case, it's just a simple p-type spherical harmonics, because we know that the nanocavity has a polarization perpendicular to the sample plane. And by this field, I convolute it with the transition density, and by making a norm, a square of it, I will get directly the photon map, which I'm comparing to my experiments. There is a code available on GitHub, which is in the framework of the Pro particle simulations that were used for the AFM simulation. But this is freely available, so from this code is also clear how exactly this is implemented.
But your bias is around a few volts, right?
Yes.
Okay.
Bias is like typically 2.5 volts, depending on which excitations you want to get.
Oh, thank you.
Fantastic. I have a lot of questions, but we don't have that much time, and we have one more question from YouTube. James, please.
Okay, so the second question from Shadi Fatayar. He says, in the PTCDA system, could you compare the photon maps of a given PTCDA assembly on a bilayer and a trilayer? Do you see changes in the map?
So thanks for this question, Shadi. The truth is that we didn't do it on 2 monolayers. And the reason is because on 2 monolayers, we get too much background signal from the surface plasmon. So that would make our analysis really difficult. But it's possible that we may try in the future. The problem is that the PTCDA doesn't have as strong signal as the tau-9. So it's more difficult to get these photon maps, even with good optical setup.
Thank you, James. James, do you have any questions? Okay, fantastic. Martin, we don't have more time, but I really appreciate. Congratulations! It's really nice and extremely clear presentation. Thank you very much.
Thank you for watching.
So maybe we could clap hands. Maybe we could clap hands for Martin at the distance. Thank you, Martin.
Thank you. So
Bye-bye.
this online stuff. Like I would just say bye to people from YouTube. Please see the schedule on the nano.ufabc.edu.br, and you see the last talk of the quadrimester. Bye, people from YouTube.
Muito obrigado pela audiência, pessoal. Fiquem, então, atentos para o seminário da semana que vem, do professor Juarez da Silva, que apresentará, então, sobre In Silico Design of Materials for Energy Applications. Ficamos por aqui e tenham um bom final de semana.